Let's now take a look at another example of the addition of angular momentum. This time we want to add two states that are going to have the angular momentum value of 1. Now this could be, for example, if we have two states and each of them have orbital angular momentum value of 1. But it doesn't really matter the nature of the state. We are only dealing with the mathematical part here. And of course, the other thing is just going to be to apply what we're learning here, but that is for later on. So what are going to be the clebsch-gordon coefficients here for this case? So let's go ahead with the exact same procedure that we did last time. So let's begin first of all by finding the total values of j. Okay, so j total. Well, the maximum value is going to be 2. That's the addition of both of these. But the values 1 and 0 will also be possible. Do not forget about them. Very important. What are the values of m? M total. Well, the values of m for each one of these will be 1, 0, and minus 1. And similarly here, 1, 0, minus 1. This is m2, and that is m1. So the total value of m, well, this can be every single combination between these values. So the maximum will be 2, then it can be, oh, sorry, there we go, 1, it can be 0, it can be minus 1, it can be minus 2. You can of course see it as well because we know from angular momentum that if our j value is 2, then we have to be able to go from minus 2 to 2 with the value of m. That's something that we knew. So let's apply, as I said, the same procedure as last time. So let's begin with the highest value of j and the highest value of m. So that would be the state 2, 2. And why do we do this? That is because in this state, there is only one possible combination that will give you this state. That's always like this. That's why we do it, because the only way that we can get this is to combine, and now remember, this ket right here, this means j value, the total j value, comma, the total m value. That's what that means. And now here we're going to use a different representation of the same situation. This is going to be 1 half, that was from the previous video. 1, 1. Here this is j1, this is j2, semicolon, and now the values of m. The only combination of values of m that will give us 2 is 1 and 1. So this is m1, m2. As I said, it is possible to use different ways to arrange these quantities. It doesn't matter. What matters is that you and, well, the person who's going to correct your tests know what you mean. So it's always good to define it at the start of the resolution of the problem. Okay, so this is the only combination. So the coefficient that goes with this has to be 1. Because it has to be normalized, so it has to be 1. There's no other possibility. And that's why we start at this either top or the bottom. You could start from 2, minus 2, because there's only one possibility there as well. However, I like to go from this top and then just go down. I think it's a bit more intuitive, but as I said, it doesn't really matter there. Now let's go for the state 2, 1. In order to find this, we need to apply the lowering operator to this quantity right here. So let's see how that is done. Just as we did in the previous video, we need to take the lowering operator, which I will call j minus or j total minus, and we have to let this act on the state 2, 2. And when we do that, we know that it's going to give us h bar times the square root of the value of j times j plus 1. So that's going to be 2 times 3, which is 6, minus the value of m times m minus 1. So that's going to be 2 times 2 minus 1, which is 1. So this right here is going to give us 6 minus 2, and that's 4, and the square root of 4 is 2. So we can actually just replace all of this with a 2, and I like to write it like this. So 2h bar. And now our ket is not going to be 2, 2, it's going to be 2, 1. That's why we apply the lowering operator, because we know that it gives us a state with a lower m. Okay. And this, of course, has to be the same than to apply the lowering operator to this state right here. So that's going to be the lowering, the j1 minus plus the j2 minus, that's the total lowering operator, the sum of these two, And this acts on 1, 1, 1, 1. And of course, the one with 1 only acts on the values for the first particle. So on M1, it does not touch M2. And similarly, J2 minus does not touch M1. Be very sure that you respect that. So here we have 2H bar, ket 2, 1. And now, when J1 acts on this system, we get 1, 1. This is unchanged. This doesn't change in this problem. So leave this 1, 1 be. Colon, and now this value will go to 0, 1. And we still have to include, of course, the coefficient that goes in front, which is H bar square root of, well, actually, maybe I will show it explicitly just to make sure. So H bar square root of the value of J, which is 1. So we get 1 times 2 minus the value of M, which is 1. So 1 times 1 minus 1, which is 0. So the second part is 0, and this part right here is 2. So we get square root of 2H bar times this state. And now we apply the second lowering operator to this state. However, the value of M is the same, so we will get square root of 2H bar as well, times 1, 1, 1, 0. And now let's divide all of this by 2H bar, so we get ket of 2, 1. This is equal to, now we have square root of 2 divided by 2, and we can factor that out of this system. So we get 1, 1, 0, 1, plus 1, 1, 1, 0. And square root of 2 over 2, this is simply 1 over square root of 2. You could leave it like that as well, but I like to write it like this. Once again, it doesn't matter, it's the same, but I prefer to write it like this. So now we have found the coefficients for this state, being 1/2 for this one, 1/2 for this other one. Now let's go to the next state. So let's go for the state 2, 0. So 2, 0. And now to find it, of course, we need to apply the lowering operator to 2, 1. When we do that, we get H bar. So H bar square root of, now the S plus 1 is still going to be 6 minus, and now when we do this M part, it's going to be 0. So minus 0, so we get square root of 6. Because 1 minus 1 is 0, so the second part is 0. And this is acting on 2, 0. And this is equal to 1 over square root of 2. Please do not forget this quantity, this number right here, okay? Otherwise your coefficient will be all messed up. So we have to go by step here. Okay, and now we have to apply the operators to this one. So let's begin by applying the first operator. Remember, there are 2 operators that have to act on each one of these states. So let's begin with the J1 minus, so the lowering operator for the first particle. So we have H bar square root of, it's still going to be 2 because 1 times 2 is 2, minus, and this time our M is 0. So once again, this part will be 0. And times the state 1, 1, minus 1, 1. And you can see, of course, that here these values of M add up to 0, which is what we expect. Just as before, they added up to 1. That's what has to happen. If it doesn't happen, you did something wrong, you need to check your work. Now let's apply the second lowering operator to this state. So we get, once again, H bar square root of 2, because the second part will be 0, and we will only be left with 1 times 2, which is 2. And then 1, 1, 0, 0. These values of M also add up to 0. Now let's apply both of the operators to this state. Here we get, let's see, actually no need for that, H bar. Here, when we apply the first one, we will get square root of 2 as well. And our state will be 1, 1, 0, 0. And finally, for the last one, we will also get H bar square root of 2, 1, 1. And this time the 1 here stays put, and we change the other value. Okay. And now take a look at what we have here. So let's do a few things. So let's divide by the square root of 6 and also by H bar. So we get 2, 0 This is equal to 1 over square root of 6. And notice that each one of these terms has a square root of 2. So that is going to cancel out this other square root of 2. So we will be left with 1 over square root of 2, the state 1, 1 minus 1, 1. And now we have 2 times this state right here. We have 1 time here and 1 time here. So this will be 2 times 1, 1, 0, 0. And finally, we have 1, 1, 1, minus 1. Okay, what next? Now well, this is it for this state actually. We have every single coefficient here. So the next step is to find the coefficients for the state 2, minus 1. To find that, exactly the same procedure. You can see we're not doing anything hard here. It's just somewhat annoying, but it's not hard. So let's apply the lowering operator now to this state. When we apply the lowering operator to it, s minus, well, s, I just did the other video, that's why I still have the s in my head. It is total j minus acting on 2, 0. That's going to give us h bar square root of 6, 2, minus 1. And now we have to let the total lowering operator act on each one of these states here. So we get 1 over square root of 6. And what do we have now? When we let the first lowering operator act on this first state, see what happens. We get 1, 1, semicolon, minus 2, 1. And even though minus 2 is of course an allowed value for the total angular momentum, it is not an allowed value for these individual states themselves, so these individual particles. So this state is going to be 0. So that part will be 0, and we will be left with only the part when the second lowering operator acts on this first state. So we'll have h bar square root of 2 once again. It's the same calculation over and over again because m so far has either been 1 or 0, and in both cases we get that the second part of the square root of 0. That's why I have not been showing it all that much. And the state will be 1, 1. Whoops, I didn't write the 1. 1, 1, semicolon, minus 1, 0. Once again, m adds up to 0. Everything is fine. And now we apply the lowering operators to this. So we get plus 2 times h bar square root of 2. The m's are 0, so it's fine. There's nothing else apart from this 2 here. 1, 1, minus 1, 0. Do not get confused with the changed value of m. Okay, here you have to put the value of m before it changes. Very important. Now we apply the second lowering operator to this. So we get 2 h bar square root of 2, 1, 1, 0, minus 1. And finally, we have to apply both operators to this. So when we apply the first lowering operator, we get h bar square root of 2, 1, 1, 0, minus 1. And the second state will be 0 because that means that this value of m would get to minus 2, and that is simply not allowed. Okay, so now let's divide by what is with this ket. I want to change colors here. So we get this ket 2, minus 1. And maybe let's just go to the next page, and that way we can do this without worrying about space. Okay, so this ket 2, minus 1 is going to be, well, the h bars will cancel out everywhere. H bar, we can factor out a square root of 2, and the 6 will cancel out, so we get divided by 6. Now, what else do we have in here? So we get, I see 1, 1, minus 1, 1, and here's another one, 1, 1, minus 1, 0. I said 1 before, it was 0. So these first two are the same, and these other two are also the same. So we get 3 square root of 2, factor out the square root of 2, sorry, that shouldn't be there. 3 times 1, 1, minus 1, 0, plus 3, 1, 1, and then 0, minus 1. So here we can simplify, of course, the 6 with this 3, so we get square root of 2 over 2, which is simply 1 over square root of 2, times the state 1, 1, minus 1, 0, plus 1, 1, 0, minus 1. So now we have found the coefficients for this other state. We have one more state to go. So maybe let me just get rid of this so I can write it down here. Well, we have more state to go for, of course, the value of total j equal 2. We still have more work to do after that. So let's go now for 2, 0, which we get by applying the lowering operator to 2, minus 1. So total lowering operator acting on 2, minus 1. This gives us h bar square root of 6 minus 1/2, so plus, minus 1, so plus 1. Then we have minus 1 minus 1. So this is minus 2, so we get square root of 4 in here, which is simply 2. So we get, let me erase it. Yes, we get 2 h bar times 2, minus 2. Okay, and now let's take a look at the right-hand side. So this quantity has to be the same as applying the lowering operators to this part right here. So we get 1 over the square root of 2. And now, if the first lowering operator acts on this, m will once again go out of our range. So that's going to be 0. So only the second lowering operator will give us a non-zero result. So h bar square root of 2, once again, 1, 1, minus 1, minus 1. And then we have, on the second one, only the first lowering operator will give us a non-zero result. So h bar square root of 2, 1, 1, minus 1, minus 1. And here we can factor out the square roots of 2 and divide by this quantity. So we get 2, minus 2 is going to be 1 over 2. And both of these states are the same. So we get 2 times 1, 1, minus 1, minus 1, which is simply this state with a coefficient of 1, which makes sense, of course, since we know that, well, there's simply one state, only one possibility, so in order for it to be normalized, its coefficient has to be 1, nothing else. So we have now determined every single coefficient for these states. Whoops, I did not mean to do that. So let me now just quickly take them all and write them down in this page, because so that we can see the result. Just all of them together. So this is 2, minus 1, then 2, 0, which is right here, then we have 2, 1, which is right here, and finally 2, 2, which is this one. Okay, amazing. Now let's continue and go for the state for which the total j is 1. So let's go for the exact same procedure. Highest value of j, highest value of m for this case. So if we take the highest value of j, that means 1, 1. Right? This is j total, this is m total. And what state do we have here? Well, this is going to be, of course, our system has orbital angular momentum 1, or angular momentum, it's not necessarily only orbital, 1, 1. And what states would give us this configuration? Well, it would have to be 0, 1, and then some other 1, 1, 1, 0. The problem is that we don't have only one state anymore. So we have to put some coefficient here that we don't know immediately. Before we knew that it had to be 1 because there was only one possibility. Now we have two possibilities. So we need to determine these a and b. And this is actually why we start with the highest value of j, because that will be only have one state. And now we can use the result that we saw previously. And this is actually the same that we did in the previous video. So to find a and b, we need two conditions here. We need one, the normalization condition, which basically means that 1, 1 as bra, 1, 1 as ket, so the inner product, of course, has to be equal to 1. And also this state has to be orthogonal to the other states. And here we are going to use that. We have to do this with a state that has the same vectors. So let's take a look at our results. If we see 2, 1, it has 1, 1, 0, 1, 1, 1, 1, 0, which are exactly the same vectors that we are dealing with here. That's why we will choose that vector, because when we apply this inner product, these ones will be normalized, so we will get some condition for a's in order for those states to be normalized. All other states, 2, 2, the other ones will be obviously trivially orthogonal and they don't give us a condition. So this has to be equal to 0. So let's apply each one of these. So when we use this first one, exactly as we did in the previous video, I did it more explicitly there. Here I'm just going to do it because we know that if the bra of the states and the ket of the state multiply, basically the inner product, it's going to give us 1. So we get a squared plus b squared equals 1. This comes for the first condition. And if you're unsure, just multiply, because of course the bra of this, ket of this will be 0, bra of this, ket of this will be 0, and only bra and ket of the same form will be 1. From the second condition, now what do we get? It's actually going to be the same, except that instead of a and b, it has this 1 over square root of 2. So when we do the multiplication, we get a over square root of 2 plus b over square root of 2. This has to be equal to 0. So from here, we can see that a has to be equal to minus b. So when we plug this over here, we get that 2 times the square root of a has to be equal to 1, or that a has to be equal to 1 over square root of 2. This could also be positive or negative, but because b has to be the opposite sign, it doesn't matter which one it is as long as b has the opposite sign, okay? So these are our two values. So it's going to be 1 over the square root of 2. 1 over the square root of 2. And now b, of course, has a minus sign, so do not forget to change it. Minus 1 over square root of 2. Okay, and now we can use this as a starting point to find all other states. So we can now use the exact same procedure that we used before and find ket of 1, 0 by using the lowering operator on this right here. So when we do that, we get h bar square root of 1 times this plus 1, so we get the square root of 2 minus 1 times 1 minus 1, so that part is once again 0. And this is acting on 1, 0, since the value of m here is reduced by 1. Now this is going to be equal to the lowering operators acting on both this state and this state. When the first lowering operator acts on this, we get, well, let's factor out 1 over square root of 2, by the way. So when the first operator acts on this, we get h bar square root of 2 acting on 1, 1 minus 1, 1. And now the second lowering operator acts on it, and we get plus h bar square root of 2 acting on 1, 1, 0, 0. Once again, they are all adding up to 0, so everything is checking out. And now for the second one, we get minus h bar over the square root of 2. And when the first one is the one acting, we get 1, 1, 0, 0. And when the second lowering operator acts on this state, we get minus h bar square root of 2, 1, 1, and then we get 1, minus 1. So now actually we can see that a few things cancel out. So first of all, when we divide by this, all of the h bar square root of 2 will cancel out. And also now we have these two states that will cancel out. So let's now find this 1, 0 ket. So this is going to be 1 over the square root of 2, this one. And then we have ket 1, 1 minus 1, 1. Then minus 1, 1, 1, minus 1. We can see that even though this right here was a possibility, it actually cancelled out and it is not present in the final result. Now let's go ahead and find the state 1, minus 1 by applying the lowering operator to this one right here. So when we apply the total lowering operator to this, we get h bar square root of 2, 1, minus 1. This is equal to 1 over the square root of 2. And now when the first lowering operator acts on this value of m would go to -2, so that's not a possibility, so that part is 0. So we only get the second lowering operator acting on this. So we get, we get h bar square root of 2 acting on 1, 1, minus 1, 0. And then we have minus h bar square root of 2, and when the second lowering operator acts on this, it's 0, because this one goes to -2, which is not allowed, so we only get the effect of the first one. So we get 1, 1, 0, -1. And here, once again, we can simplify a few things. So the h bars and the square root of 2 will cancel out. So what we will be left with is that 1, -1, the state is going to be 1 over the square root of 2 of 1, 1, minus 1, 0, minus 1, 1, 0, -1. So this is actually our end result here. So let me now get rid of all of the intermediate steps that we had so that we can leave here only our results. So here we have 1, 1, 1, 0, and 1, -1. However, there is still one state that we haven't calculated, and that is of course the state for 0, 0, which of course this means that the total j is 0, and this means that the only allowed value of m left is the one where it is 0. Now, what possible combinations can we have for this? So we have to take some normalization constant times one of the possibilities, which is 1, 1, because of course our particle or system, it hasn't changed. And then we can have it be, for example, we can have it be -1 and 1. We can also have it be some other normalization constant times 1, -1, and we can also have some other normalization constant times 0, 0. These are the three possibilities. So now we need 3 conditions, and it will actually be very similar to before. So one condition will come from the inner product because this state has to be normalized. Condition number 1. Condition number 2 will be because this state has to be orthogonal to the other states that have these same vectors. Now, which states are those? For example, take a look at this. 1, 0, it has -1, 1 and 1, -1, which are some of the states that we also have here. So 1, 0 has to be orthogonal to 0, 0. The third condition we will see when we go back a little bit and take a look at the state 2, 0. It has the same 3 vectors that we have here. So 2, 0 has to be orthogonal to 0, 0. And this is of course why, as I said before, we start with the highest value of j and then we move our way down. That's why we also, after 2, we have to go for 1, because otherwise we would get to this and we wouldn't have this state, so we'd have to go back. That's why we do this in this order. Now let's go for each one of these. So this one is quite simple. We use the inner product of this state with itself. Each one of these is going to be 1 when it has the inner product with itself, and the inner product with any other state will be 0. So we're left with a squared plus b squared plus c squared is equal to 1. From this one right here, let's take a look at what 1, 0 is. 1, 0 only has these 2 states, nothing with a 0, 0. So it's going to be 1 over square root of 2 with the one with -1. So let's go ahead and undo this product maybe, so it's a bit easier. So it only has a state for -1 and 1, and this one right here. So we'll have a square root of 2, 1, 1, -1, 1, 1, 1, -1, 1, right? Because 1, 0 is, yes, we took this part right here, and then the other one has a minus sign. So we get minus this part. So we get minus b over the square root of 2, 1, 1, 1, -1. And this has to be, and this is of course the inner product. I only wrote part of it. This is 1, 1, -1, 1, 1, 1, minus 1, 1, and this has to be equal to 0. So this right here is 1, this right here is 1. So we are going to see here that A has to be equal to B. And finally, from the third condition, this we will do it in the exact same way. So this state, the ket of this, will multiply the bra of the other one. So, and only when this one is multiplied with the ket 1, 1, minus 1, 1, and similarly for all the others, will the result be non-zero. So let's take a look at this first term. So we get 1 over square root of 6 times what? So we get 1 over the square root of 6 times, this state was, I think it was this one, minus 1, 1, so it's going to be times A. What else do we have? Then we have the state 0, 0, which is 2 over square root of 6. So the state 0, 0, well, here we have a c, so we get plus 2c square root of 6. And finally, we have that the last state is just 1 over square root of 6. So we get plus 1 over the square root of 6 times c. And all of this has to be equal to 0. Wait, I'm missing the b here. Sorry, I think that I made a mistake here. So let me just... So what is now the second part? So the second one is this one right here, which is, let's go for the one with 0, 0. So that's going to be 2 divided by the square root of 6. And that part will multiply the one with a c here. So it's plus 2c divided by the square root of 6. And finally, we have this ket right here, which is just 1 over square root of 6. And that's going to multiply this one with a b. So it's going to be plus b over the square root of 6. And this has to be equal to 0. So our system of equations is going to be a squared plus b squared plus c squared equal to 1. And then we know that, what was the second one? A has to be equal to b. And also that, let's see, this one, well, we can just multiply by the square root of 6, so it is simplified. The last one is a plus 2c plus b is equal to 0. Okay, and since we know a is equal to b, we can plug it into this third equation. So we get that 2a plus 2c is equal to 0. So a is equal to minus c. So we can now put all of this back in here. So we will see that 3 times a squared is equal to 1, which means that a is equal to 1 over 3, plus or minus, of course. And what else? Now we will have, well, what are the values for the other one? So b will have the same value and a will have a different, the one with the opposite sign, c I mean. So let's just take the positive value, since it doesn't matter, it will make no difference in the end. So let's take a positive value, so this is going to be the same as b, and c will then be minus 1 over the square root of 3. So let's plug these values back in. So let me get rid of all of them. So this is a minus sign, and I will factor out this 1 over square root of 3. And this is our result. This is it. We have found each and every single coefficient for every single possible state of this system. So if you have any questions, let me know. But as you can see, this is quite a simple procedure. We just start with the highest possible value. We have to determine what the possible values of j are, what the possible values of m are. Then we start with the highest ket, and we just apply the lowering operator over and over again. And when we are done with the states of j equal 2, we then have to take the highest value of the next highest value, which is 1. We apply the lowering operators, but first, of course, we need to find these coefficients, which we find through orthogonality and normalization, and it's the same over and over again. If it's j equal 3 or whatever, or 2, or it's larger than this, it will simply be longer. You will get a system of equations for your coefficients that will have more equations, but the idea is going to be the same. So I hope that this helped you, and I will see you in the next video.